everyone and welcome back. So in the last part we talk about hydrocarbon migration and drainage. We learned that hydrocarbons can move through the rock and enter our reservoir. But now think about this. If oil and gas keep moving upward, where do they finally stop? And another question is what happens to the water that was already inside the reservoir today? Today we are going to answer this question. We will talk about hydrocarbon trap, connect water, free water level or FWL and the transition zone. So let's start with the first one. So okay, let's imagine something. You have a bottle and you put some oil inside it. The oil can move around, right? But if the bottle has closed cap, the oil cannot escape from the top. Something similar can happen underground. We know that hydrocarbons tend to move upward, but if there is suitable geological structure that stop them, they can collect there. This is called hydrocarbon trap. So, in a very simple words, a trap is a place where oil and gas can collect and stay underground, and this is very important in petroleum geology because if there is no suitable trap, hydrocarbon may continue to move and may not form a useful accumulation. Now, our trap needs another important thing, seal. Let, let's make it simple. Imagine you have a water bottle. The bottle holds the water and the cap stops the water from escaping. In a reservoir, the reservoir rock provides space for hydrocarbon to collect and the seal or cap rock helps stop them from moving upward. So remember these two words, reservoir, store the fluid, seal, helps prevent their escape. That's the basic idea. Now, do all traps look the same? No, they have different types of traps. For now, we will keep it very simple. The two main types are structural trap and stratigraphic trap. Structural trap forms because the rocks have been folded, faulted, or deformed. For example, imagine an anticline. It's look a little like a upside down ball. Hydrocarbon can move upward and collect near the top. Another example is fold trap where upward can change the pathway of fluid's movement. Then we have a stratigraphic trap. These are related to change in the rock layers. For example, a permeable reservoir rock may change into a less permeable rock. So the main idea is simple. Different geological conditions can create different types of traps. Now let's come back to our water. Remember what we learned earlier? The pore space was originally filled with water. Then hydrocarbons entered the reservoir and started pushing some of that water away. But did all the water leave? No. Some water can still remain inside the tiny pores. Let's imagine a sponge. Take a sponge and completely soak it with water. Now add some oil. Will every drop of water disappear? Of course not. Some water will still remain inside the tiny spaces of the sponge. The same basic idea helps us understand that happens inside a reservoir. Some water remains in the pore spaces even after hydrocarbon enter. This is remaining water is related to Connate water. So, what is Connate water? In simple words, Connate water is water that remain inside the reservoir pore spaces. It can stay in smaller pores where hydrocarbon cannot easily displace it. This is important because the reservoir is not simply 100% oil or 100% gas. They can also be water. So when we study a reservoir, we need to know how much pore spaces contain hydrocarbon and how much contain water. This is where fluid saturation become important. So remember, hydrocarbon reservoir does not mean there is no water. Some water can still remain inside the rock. Now let's talk about free water level or FWL. This is one sound complicated, but the basic idea is actually simple. Imagine a glass with oil and water. What happens? When the oil sprays about the water because oil is less dense. Now imagine this situation underground. There is a level that we use a reference for the free water part of the reservoir. We call this free water level or FWL. It helps us understand how fluids are distributed vertically inside the reservoir. So don't worry about memorizing a complicated definition. Just remember FW is an important reference level for understanding reservoir fluid distribution. Now again imagine we cut the reservoir open and look inside. What we see at the upper part, hydrocarbons are more dominant. Why? Because they are lighter than water and tend to move upward. As we move downward, water becomes more dominant. But there is something interesting here. The change is usually not sudden. We don't simply have oil here and water spreads immediately below it. There can be gradual change between the two. And this gradual region is called the transition zone. Okay, let's understand the transition zone with a simple example. Imagine a wet sponge. If you look at the sponge from the top of the bottom, the amount of water may not be exactly the same everywhere. Some areas may have more water and some may have less. Something similar happens in a reservoir. In the reservoir zone, water saturation gradually increases as we move downward at the same time. Hydrocarbon saturation gradually decreases. Why does this happen? One important reason is maybe capillary pressure. Remember our first part, we talk about tiny pores and capillary forces. These forces can hold water inside the rock. So the transition zone is basically a region where water and hydrocarbon saturation change gradually. Okay, guys, now let's put the whole story together. We started with a reservoir that was mainly filled with water. Then hydrocarbon was generated in a source rock. They started to migrate because hydrocarbons are generally lighter than water. They move upward. Then they entered the reservoir and started displacing water. That's our drainage process. If a suitable trap was present, the hydrocarbon could accumulate. But remember, some water remain inside the rock. This is a Connate water. And when we look at the vertical fluid distribution, we have an important reference level called the FWL. Around the hydrocarbon water transition, we can have a transition zone where the fluid saturation change gradually. So the whole story is migration, then trap to accumulation and accumulation to fluid distribution. Now the picture should be much clearer. Before we finish, let's do a quick review. What is hydrocarbon trap? It is a geological condition where hydrocarbon can accumulate. And next is, what does a seal do? It helps prevent hydrocarbons from escaping. And then what is Connate water? Connate water it's water that remains inside the pore spaces. And that what is FWL? So it is an important reference level for understanding fluid distribution. And what is the transition zone? It's the region where water and hydrocarbon saturation change gradually. If you understand these five ideas, then you have understood the main concept of the today lecture. And that's it. We have now completed lecture 4, Alhamdulillah, physics of reservoir fluid filling. We started with the water filled pores, then we learned about hydrocarbon migration, drainage, hydrocarbon trap, Connate water, FWL, and finally the transition zone. So now we have a much better idea of how oil and gas water are arranged inside a reservoir. In our next lecture, we are going to talk about something very important, maybe porosity. What exactly is porosity? How do we calculate it? What controls porosity? And why is so important for a reservoir? We will answer all of this question in the next lecture. Thank you so much for watching. If you enjoyed the lecture, don't forget to like, subscribe, and turn on the notification bell. I will see you in the next lecture 5. Porosity. Allah Hafiz. Remember in your prayers.